what is the difference between transfer learning and our proposed transfer learning plus CNN architecture? It's pretty straightforward that what happens in normal transfer learning is that we pick some particular model, pre-trained weights, and fine-tune our custom data on those weights, on those models, right? But what we are doing here is like we are trying to in addition to the existing pre-trained architecture, we add additional convolution layers to those. For example, let's say we pick a ResNet model, we add additional convolution layers to those before the fully connected layers, and this is basically our transfer learning plus CNN architecture. So in particular, we use 8 layered convolutions layers in addition to those pre-trained weights, and then train our imbalanced data set on this architecture. And we experimented with 8 different pre-trained weights, ranging from VG16, EfficientNet, ResNet, DenseNet, MobileNet, GoogleNet, and ExceptionNet. And we compared it with just convolution CNNs as well. I mean, like we experimented with just convolution layers as well, not the pre-trained weight, as like removing the pre-trained weight. And how are we resolving this this imbalance problem in particular? So as we mentioned that we experimented with focal loss and cross entropy. I mean, like, as we know that cross entropy basically increases the loss as the predicted probability diverges from the actual label. But what happens in focal loss is that like it downweighs the easy samples and focuses on hard samples by a particular constant. And we experimented with other balancing methods in addition to standard augmentation, is SMOTE and Edison. What happens, SMOTE does is like it applies the k nearest neighbor approach, where it selects those k neighbors and joins them and creates additional synthetic samples. Whereas Edison is almost similar to SMOTE, but it uses a density distribution to decide the number of synthetic samples to generate. So this is our like the methodology that we used. Now moving towards the results and comparison section. So as we can see from this table is like among all of the models that we experimented with, VG16 along with CNN performed the almost very best in compared to the other architectures like EfficientNet or GoogleNet or MobileNet. As with the standard cross entropy loss, we saw that our accuracy was obtained about 83%, whereas when we replace the cross entropy with focal loss, we're almost getting 85% accuracy. This is the increment, and this is our hypothesis proving correct that having a focal loss which basically downweighs the easy samples and focuses on hard samples, hence resolving the imbalance scenario using focal loss. However, when we experiment with those balancing methods like augmentation, SMOTE, and Edison, we see that augmentation almost performs the best, like compared to any other method, with about 96% accuracy, compared to SMOTE and Edison with about 86 and 87% accuracy. And in terms of other metrics as well, like precision recall and F1 scores, as can be noticed from these graphs, data augmentation almost performed much better than in all of these metrics compared to cross entropy or SMOTE or Edison. Focal loss compared to cross entropy performed better as well. So as a conclusion, we conclude that VG16 transfer learning CN model performed the best overall compared to any other, and we can even further improve the accuracy of VG16 by performing the hyperparameter tuning and extensive grid search CV in future. And other future work that we would like to explore is like to increase the performance of lightweight models like MobileNet, as it will be much more applicable in real world scenarios, since real world scenarios deal with deployability, and these kind of models, exploring these kind of models would be really practical to deploy. Thank you so much for listening to me. If you have any further questions, please feel free to ask. Thank you so much.
Then you can, this should be the version of the file.
Maybe we can all go to the coffee break, no? Try to get in the fourth.
Let me check the program. Yes, the plan was at 4:04 it was coffee break, so we can go now until 4 o'clock. So we do coffee break now until 4 o'clock. We come back here after. Thank you.
Yes. Coffee. Yeah.
Yes.
Yes, please.
This about this. Yeah, yes, yes. You're anyway, right?
Good morning.
It's above.
Oh yeah, coffee break is interesting.
I agree. They're the ones that have the time. Nice. How was the poster session?
Very beautiful. You missed just one. We didn't show. And we missed one paper presentation. That's why we are in front of the line,
Okay.
not behind.
Yeah, you were very in front. It was supposed to start. It was supposed to start. Starting at 3:30.
Just moved half an hour.
Yeah, so you could be finished half an hour early.
Yeah,
Yeah.
maybe even earlier because we are not sure about the model.
Okay.
Just agreement that we have some one of us. But he will try it, but it's our third.
Yeah, yeah. Kids come first, yes.
Yeah.
Yes. Kids come first.
That's our topic. Also.
Uncertainty, oh, yeah. that'd be good. At least you got coffee now.
But we have time, it takes no time. Yeah, 30 minutes. No, the organizer startup, like, it will be here.
Oh,
They don't have any other place.
that means everybody's coming.
I think so.
Yeah. So those posters should be getting up.
Yeah.
You might get
No,
knocked over.
Laura is-
So, Sarah, okay.
No,
No, we're happy you're here. We're happy.
I don't know what's happening, but suddenly they decided to do the.
Yes.
competition.
Yes. Well, do we have our helpers with us? Should we take the easels off? Should we take the easels off the table and everything? Since he has all this?
Yeah.
Yeah, helpers.
Yes.
Helpers.
Guys,
Helpers. Yes. We
Call them volunteers.
Volunteers.
They haven't really.
Yes.
volunteered, They have been.
Yes. Yeah, the coffee's going on the table. It's not like that. They need the coffee. The table for this.
no, just put them.
Okay. Then we can just. Right?
Yes.
Oh, that's good. If that was a bit more, then. we have another.
And
Okay, I was a bit worried because I was like, so complicated.
So you know, even if that. Let's see if we can get it.
We have to. Yeah, that's I would down. It ain't much, but it's other point.
It's coming. Yeah. Yeah, I'll sit again. Yeah.
Oh, yeah. They will get to the cups. It's very interesting. Io posso anche non preoccuparmi se gente sta a casa per Very wrong. Hi, Pittsburgh, big venue. Yeah, the UAI Cups. Yeah, yeah. I think they might even have some national organization.
Yeah.
Where was that young lady in Texas? So. Upstairs, all like. Yeah, upstairs and all the way. They
I'll let it go in 1 minute, but that's.
Yeah, that's the best thing.
No time for.
Desperate times, desperate needs, I guess. Yeah, and you need to keep your own cup.
Yeah.
Yeah, no, where they come from, you know. Yeah. I'm good.
You can get from this like the whole sentence, but that's gonna be like point.
Yes.
You can.
Yes.
They tried a little bit. No, that's not fine. Like if you say that.
There are some research centers.
They probably did it.
Cambridge.
Cambridge, I actually was interviewed. So some of them can do that. Is asking ChatGPT.
I could think that it's
more now. Number of same words in the students to see if they are. I'm getting that. But maybe this would be.
You get a chance to. At the time, they're sitting.
How are
So
you?
it's sold by some people have their own cups.
Just.
I got you one, but.
Are they want somebody understand?
Remind me again, where are you?
But then I think this is subsequently this research and
First year, but.
Huge house with three bedrooms and 3.5 bathrooms. Honestly, 3.5. Yeah, like she can switch. And like the bathroom thing.
Yeah, I
really
think
threw me for a-
like the half bath.
The 3.5 bathroom.
That was
literally a-
Yeah, the half.
I was thinking how big this
It's
house.
that when you go to visit.
No, we all go to visit her now. No, it's not.
It's just you stay overnight, then you have your.
She was bathed in the river. Probably.
My parents. And 3 bathrooms, whatever. They're like 2-3 foot, right? So that's why they did. That's why they did.
Yeah, also the living in a one bedroom.
So you're on your own. More concerned that you have to be clean. It's a lot.
That's the first thing I asked. I think somebody could bring. First question, huh?
Why is the same? In terms of.
It's like.
It's in a row.
It's a row house.
In a shape.
Yeah, yeah. But the thing is, just like, you know, these fancy ones that have these things hanging and one of them is for the lights. And it's always really cute, but not in my house. Like, you say, no, it's just something, but
Are you sure that was nothing with this, that you needed to figure this? Yeah.
So the light was controlled by this. So there was like one thing.
Learning the language.
Yeah.
You figured out the power of this system.
And they.
Yeah, I didn't my personal.
That's actually.
Well, yeah, it says maybe. They care.
Yeah, fine, no, no.
Yeah.
I might still do this song. So I will do it.
There's like some.
To be fair, I think it might be.
Yeah, let's get some then. Well, leave it.
So you can know.
I think they can call that. It's the same answer.
Actually, when I saw you were talking, I took it up on that. So I didn't see the conference. I did it.
I know so many people.
Yeah.
No?
Yeah, it's just really cool.
There's some scared.
Yeah, I know.
Good care.
But you could do it.
Like when I, at the beginning, I thought.
So we can use this copy.
Then it got in my mind completely.
Here you go.
Messed up, but I could actually stop. and say, okay, hang on. Moment to just,
But I'm not doing it. I'm not a doctor.
Horrible idea for those who.
Exactly. We don't, yeah, because apparently they don't even know that they should bring the cows.
They will come, they will come at 4. Because our weight was at 4, so we just. Changed it.
But they also
Yeah, man,
all
I
the
know.
copies in this room for everyone.
Yeah, he said.
That's, but he had 2 places, right?
Like the other.
He said there is no any other room.
Yeah, that's what they told as well, but then another guy said that maybe they do so. I don't know, man. It's like people say random things happen. I don't know. I just give up. I give up. Okay, just to be clear, the workshop workshop organizers that there would be times for doing coffee. That's, and everybody choose like a slightly different time. Somebody starts at 50, somebody starts at 10, somebody finishes at 10. I don't know, man. I don't know.
I guess the question.
No, you do it, but you know what will happen. As organizers, you have to push people out.
So.
Also, it's not my preference that we have a coffee break in a dedicated room. I would like them to be somewhere else, but it's not me to decide.
Okay, say mostly not, so we had in the speaking about the Zoom link didn't work.
What is climate change compared to this?
You know, every time I say something, it says, Sarah, you have to stress. It's like, nothing is working. It was my fault.
Yeah.
Not my fault.
No, I just.
You find it funny. I mean, I don't know. I'm supposed to only do Zoom. I'm not an lecturer. She's a workshop chair. None of us are going to. We don't know anything.
I see.
Because it's the boss.
Like, I'm okay.
You have finished half an hour early.
Yeah.
So that's why.
Okay.
Yeah. Razzie, who did you ask for the cups?
Here they are. Here they are.
Razzie, did you ask?
Yeah.
And snacks. Snacks will be ready in 5 minutes, within 5 minutes.
Next, wow.
No problem.
Are you still surviving? I'm taking care of everything.
Yeah.
Are you here? From. Are you still in?
You put snacks. Where do you put snacks?
Where are you for real?
Oh, we could ask.
Nice,
I guess we should.
Yeah, back home.
No, guys, what are you talking? Do you know who this does? Nobody. And this is my space for that. If they come with the stuff, what do you do?
How long is your break? Okay,
We anticipated it because there were 2 or 3 points on this one. So that's what this is.
they'll come.
Because we have the chairs there.
Okay, Nick. They can.
But it's not in private, so that we can be. That's fine.
Yeah. Yes, to send it. I told you, I think I should.
No, the other thing is,
So we.
you mentioned it last night.
Okay,
Yeah.
see, we have, can you read the, right, can you remember the IHDRs for the trajectory data? Yes, basically, yes. Yes. Try conformal methods and turn out there's conformal region for language here. Yeah. So we started talking about
Online is the one that's right there.
can we compare them? Like, are there situations in which we can actually compare? Because in general, we will not be able to do that. But are there some situations? And it turns out that yes, there are. Basically, for now, what we found is that the work can be divided into 3. In one case, precise size density regions are narrower, while you're doing the same the opposite holds, and in the majority of the cases, neither holds. You cannot compare. But if you can live in one of the two of these other cases, yes. Then in one case you have the modeling effort that you put into coming up with different priors, different likelihoods, whatever is paid off, right? Because you have something small. And in the other case, you can you just don't need them. Yeah, and so having fun. I'm fairly sure of the map, and I wanted to double check. I can send it to Edgar Dobrevan, but instead, oh, I'm in vacation. Let's not later. And I met yesterday. Then there's going to get some. Once everyone has them just one by one. Once I show them that you could drop a bunch and just test the
Yeah, you'd be surprised with what this equipment can do. And this is not even a more advanced room. This is like base up, except they have 5 microphones on the ceiling. That's a little bit more advanced than other conference rooms, but the other conference rooms, they're on campus. I don't have to bring that. Yeah. Yes. So yeah, it's quite easier. And the most sophisticated ones have a choice. The preview window, computer, test computer, and you're sitting there just moving it around. That's nice. It's nice. So yeah. So we're waiting to the point where I can get one finger and do that. We're waiting. I wonder how long that would take. Everything costs money. Everything costs. So it used to become billionaires. Give back. Give back. They are. Oh, they are.
They were saying you don't get on the original plan, but no, we are.
Nice.
It would be so funny if it's an AI conference for generating images. Yeah, that would be cool to see. Yeah, so cool.
Nice. It would be. It would be. No. With Vegas, they have conference because they have the most of the technology. So I can tell you, probably do that.
Wenn man 2, 3 Tage nicht wirklich war, jeweils beim Alster am Wochenende. Ja, wascht euch mal. Vielleicht nicht waschen, aber halt. Ich würde sagen, nicht wirklich sehen, naja, danach sehen und die auch auch ein bisschen.
3D print.
Yes. Yes. You tell the difference between real and AI. Definitely need some objectives there. I don't know what projects of 3D now. Might be part of that. But they weren't used to there's perks now. Look how big they are. It's the Costco. Costco is just the same. Nice.
Yes, Magdalene and all that.
Brian. Check on.
Yeah, please. I can make them all. I'll try to.
But are there any mapping that you want?
Yeah.
We don't have any.
Yeah.
That's not bad.
It's not very good. And then I mean, they're both not only.
Yeah. Not what you intended to do, I guess.
Okay.
Yes.
Yeah, it's
Larry. Okay.
Yes.
Oh, it's on the, yes.
Yes. What the classification? Yes. I can write it down. I can make it. Actually, I can show you on the. It's very. It's easy. What is new? Is you see. So eventual neural networks already exist. So first thing we do is train the network that gives us parameters for the facial expression. Okay. Usually these guys think so. One portion of the loss is the one that's needed to give you type 2 FET, right? So the but then I've added something, and this something other people didn't have in mind this last part of so for example, I level 1
It's one of our harder days.
whereas as you know, it's 90 here. It doesn't really differentiate between So I did something there, I changed that, and that would this other extra term prevents from because that's not really tends to
So that's the hottest.
and the other you think
The hottest it was on 3 days in a row, 107 years. So yeah, so I've been.
Now
You should send
There's some down to 86.
Right, so
By 4 o'clock.
eventually you have same specified 10
It's actually not that bad.
priors, but only 5 of them are actually dependent on one another. So it's a prior. That's not So and these are the two.
But usually,
There's a little portion of them where I do the reduced version of this, where basically instead of having ambiguity or epistemic uncertainty from the beginning, from the top through the priors, I use only one prior, I obtain one posterior, and I detect. And I do so considering probability boxes. I have comma P plus X, and that plus epsilon so gives me the purposes, and all that plus epsilon is the ambiguity or the epistemic uncertainty. And that one is even easier because you instead of computing the IHDRs, the imprecise sensitivity regions, there is a result from the one who basically tells you that you have to compute the highest density region with just one distribution to obtain the actual imprecise highest density region. But you have to compute it at a different. So if you want the alpha level imprecise highest density region, you have to compute the alpha star highest density region of the predictive distribution, and this alpha star is something. He says. So I know it's very confusing, but if I write it down, that's gonna be interesting. That's it's everything went to the right piece. That's why I'm very angry that they didn't do the notifications because they had other things to do, and this would have been very nice.
I remember that you mentioned.
Yes.
Definitely. I kind of like that it's a conference of all the and still 5 days.
It's only 100
And yet a conference.
Just talk to everybody.
Right.
Like,
Yeah.
Sure. That's the only one that's out.
Yeah.
Planning on doing something that's not, but I'm not going to make it.
where are you based?
Tomorrow morning.
That is
And the night.
Family things. My girlfriend's friend.
Nice.
You just have an editing term.
Pittsburgh, London.
Right.
Yeah.
And you can just plug it in. And all of
Like a 3-hour.
just
That's one.
it's a very
Flying, yeah. Flying, 3 hours. Flying, 3 hours.
Yeah, but why could?
Yes, yes.
I mean, I'm multiplying like something.
you'll lose something here. On the other hand,
That's a direct.
Those are real. nice.
Our internal system is.
just requiring one.
I don't know, maybe.
You'll see this.
Tomorrow it's 6 hours. I really like the.
I was not sure about this.
Yes.
I'm trying to get back to you. I want to write down.
Thank you.
Thanks. And I have,
What I'm going to make is. Some 7-hour layover.
Thank you very much.
but I think
Yes. And I think I could have the gist, but let's talk more about.
No, I'm thanks to New York. So I didn't on my way to 2.5 hour layover.
It's because it's.
Lady second authors.
If I had known, I would have done it.
You can say anything about the super.
But in my son, it's now, it's now down to 5 months.
You, okay. Oh, no, you got this.
Kind of nice get also. When are you going to be where?
I'll be in there then I guess from Saturday. So you said you put
You can wait another.
I'll be honest with you.
Yeah.
Okay, so
9 a.m.
so.
Can we start the session at 4?
Yes.
4, we start with the next two spotlight.
So I think I saw.
So yeah,
Really flying out.
so I'll be.
Like seeing this.
More sightseeing day.
Yeah.
I mean, the flights.
We're gonna be just and leaving.
And
No, I'm from Saturday till Sunday. I'm in Queen and I'm gonna be in from Thursday. I never.
When I first came up here, there were people that only downtown, that was it. You know, I was thinking, it's all to get out like.
To be a lot of people, supplies, landing,
And they're boomerangs that they left for either 5, 10, 20 years and now out of business. Yeah, it depends on who you talk to. Because you're not going to.
I'm going to.
Really best thing in the world.
I'm actually skipping.
It's because I'm. It's actually not. The best thing in the world.
I know we're definitely going.
You should go to the.
And I got simply listen.
And then there is the client, which is just that. Very sensible for you. And it got drunk the first time and then he broke. We drank again. But it's not, it's just a little.
Nice.
It broke because it was just that.
It's a nice level.
Yes.
No one's buying my house.
And
Then I had family up here.
No.
So that was another.
Yeah, that's the problem.
I didn't know. And we would get them. You posting up like that.
You were going to start like 2 minutes. What the people were like putting fuel in that.
We're all coming together and stuff.
Yeah,
I can barely speak a sentence.
this time I.
And I can do it in French. Yes, because that means the city is at the national language. Yes, yes. Nice. Yeah.
I don't know if you can really call this. It's
It's a cheap zero. And we just overnight, night, evening. Of course. That's a different.
That one test at the end of the year.
No.
Yeah.
I mean, that's by. They want us to be able to.
Oh, I mean, if you have a chance, then.
Practice test would be.
It's even if it's not expensive, I mean, but less it gets more than $100. Then you have to pay off. You can find me some lots. There's a hit for this. They kind of argue different short flights. What's the long flight where you make it jet lag? There's kind of a business benefit of flying business class because you arrive less than.
That's all.
I think they kind of minimum. They put it like that. San Francisco, New York. But absolutely. Because I mean, how many times we're probably the most common business. It's pretty big. New York.
Even prior to
The drawback now of that is that London's Pittsburgh also just belong.
Yes.
Pretty much all.
Go by.
It's not no.
Big difference.
Over here, I think a lot of folks. A lot of folks. And a lot of folks. We're about a year ago, about 9 months ago, me and my wife went on to see the watches. Literally felt like it was an.
Oh, next year they will.
And they was next to us, right? And they're, we did, locally on the news. A street, half a block up, there was a street going up, we could walk there. It was shooting at a house. It's not stereotypical. Does it's doesn't happen.
Before arrive, you're already going to get
These folks know.
I also ran into not very so I see people who like games.
that's not. Not.
It's hard to find it. It's like the first one, it's hard. You've got to put the bars, but it's not possible.
Yeah, the US can be.
You sent your slides.
I don't carry anything and I walk around.
Yes.
Just said we have a couple pictures of the deer, so just. It's just.
Yeah, I see. Mark now the part of the conference from west.
It was.
Yes, yes, and his guys from the industry. So
Yeah.
very nice. No, that's fine. People will forget. I think it's in that know the skills.
Maybe they would, make a note there. And otherwise, it keep coming 2 weeks before. Yeah.
Okay.
This is also for you, right?
Yes.
Yes.
This is my first one.
You start at 4:30.
This will be. So short line students isn't it? As a but this is the I get the feeling important that I know so I had it's such an amazing
Yeah, I think it has to be. Was I not listening? That's why I just looked at this one. Push on.
And I have one file there. And then file there. Yes.
So I didn't hear.
Yes.
What's in there? We will have 10 in German, and then she will. Yeah, I mean, I hope that problem.
To make mistakes.
Really.
Open it for years.
You know, for this, you have to write this application on what's called essay. I wrote this. I don't know why.
Makes a lot of sense. It's first of all. True.
I got some message. Everything I think it's about this mark. Yeah, so like 10 things, yeah, are you missing something?
But I read a lot of stuff. My friends write very good at that. Even the foreign German, Russian German,
But I haven't, you know, that's German.
Trust me, I'm very, very confused. Sorry.
Do they like the things that people make?
So I think it's in terms
My dad doesn't speak any English like this. Just starts out in his head dialect and slower version. Nobody's gonna understand if you talk that way. He tries to talk with
yeah.
I think the other person working on it also.
Yeah.
There was a final like a year or yesterday.
It's the first time certain people can provide something. We're not just like you should be uncertain, but should be uncertain. You should actually be uncertain to talk about it. That's actually.
Say something.
How you think about that light? But you want to
He's American, but he said he can't speak actually, he declines the very better as he's the majority of my friends. But he's actually in an immediate so people who are for the rate,
But I want to do the I mean, maybe it's like the words you were also using, and maybe they would expect something different. But after some time, they realize, okay, it's a rich guy. Just
Need more speed.
yeah.
but here,
Yes, but
Maybe we can once. You have to act in simultaneously. So customers need okay, so like from this I was trying to so can you do something like I don't know, certain embedding yes,
So it's very good at motivating that. So it's not everything that's it.
right.
Then always, I mean, the same all the. It might not make sense because if you might be more and you only have to the me, it might be between the two.
He's going there.
He also in Japan.
Yes, I mean, yeah.
He also
You guys want to sit down? We're gonna start the session now, okay?
there are many
Yeah, or you could also just set it ways you want to calculate. Right. If you also Okay, we are going to start. Our next speaker is Richa, which she will talk about fair ranking under disparate uncertainty.
Hi everyone. Yeah, I'm Richa. I'm a PhD student at Cornell, and I'll talk about our work fair ranking under disparate uncertainty. This is joint work with Thorsten Hilkens, my advisor at Cornell. So actually, before I start, what this talk is not about is uncertainty quantification in machine learning models or learning of uncertainty or even reducing uncertainty. Rather, in our paper, we highlight how differential epistemic uncertainty between machine learning models between groups of options can cause unfairness and a certain type of unfairness. And then we present a solution to provably correct for that disparity. So to motivate the setting, we operate in this constrained resource allocation setting. And there's numerous examples of these settings. Some of them are hiring, college admissions, medical trials, and marketing campaigns. And in all of these settings, there are N candidates, and there's usually a principal, a human decision maker, a human evaluator, and they have to select top K candidates. And ranking is very commonly used in these settings to focus to make the principal more effective by presenting them with a manageable set of options. So this, I'll illustrate this with a toy example. So we have a population, and in the population, there are two groups of people, orange and blue. And both the groups have the same total number of candidates. So there's 2,000 candidates in both the groups. The relevance, which is Ri, it's binary 0, 1, 1 for qualified and 0 for unqualified. In the orange group, it's Bernoulli 0.5. In the blue group, it's very sharp. So it's either 0.1 or 0.9. So obviously the model is very informative about the blue group, but completely uninformative about the orange group. But note that the expected number of relevant candidates in both the groups is 1,000. So now when the principal has to select top K candidates, top 4, top 10, top 50, they'll go down the list of the probability and they'll only select candidates from the blue group. So there'll be no candidates selected from the orange group at all. And this is unfair to the orange group. So specifically, this is due to what we say is disparate uncertainty between the groups. So we start with any Bayesian machine learning model, which is trained on the features of the candidates. And taking this model induces a posterior predictive distribution. We take the expected posterior predictive mean, and usually the standard Bayesian update procedure, it accounts for model uncertainty in the model parameters, but there's still differential uncertainty between the groups. And it could be due to the less number of samples, the model was trained on less historical data for this group B, or that this group is missing some features like the underrepresented minority groups. They may not have like grades for AP credit. The school just didn't offer AP classes. So and one thing I've noticed that this high uncertainty doesn't mean that there aren't relevant candidates in that group. But if we never surface them in the ranking for the principal, then the principal doesn't have a chance of evaluating. So this is the probability. I'll go through a probability ranking principle in 1997 by Robertson. It's probably the most effective thing to do from the point of view of principal. And so there's again these two groups, 0.5 relevance probabilities for the orange and then very sharp for the blue. And so they'll go down the list, they'll select these top 3 candidates. And then the actual merit of the candidates is revealed. So the green box is the qualified and red is the unqualified. And there's 3 qualified candidates in both the groups. So now we ask this question, what is the cost burden on each of the stakeholders, so the two groups and also the principal. And cost of opportunity has been studied in the literature in classification settings. There's some work in ranking settings. We define this, we formulate this cost of opportunity as the expected fraction of relevant candidates that didn't get selected. So it's very related to the popular recall K metric in information retrieval. And it's the cost of missing out on the opportunity to be selected, on the opportunity to be selected when the candidate was truly relevant. So if you look at this example, there was no candidate selected from the orange group, so they bear 100% of the cost burden. So we normalize it with the total expected relevance of that group. So the cost burden on the orange group is 1. The cost burden on the blue group, it's almost 0, but we take the stochasticity of the relevance. So it's a little more than 0.0, 0.05, because it's 0.95, there's a chance that the candidate wasn't relevant. And then the principal also bears the cost because they didn't select some candidates that were truly relevant. So now, clearly, there is uneven cost burden among the different stakeholders. And we asked, what's a possible solution? So a natural solution that comes to mind is random lottery, fair lottery. And this is, you select the candidates, no regards to relevance, no regards to the group membership. So say there was a sigma uniform, one instance of uniform ranking, it selected these 3 candidates. Again, same thing, there's 3 relevant candidates in both the groups. And now we look at the cost burden by the same definition. So the costs are more evenly distributed, definitely evenly distributed, but they're much higher because uniform policy, as you would think, doesn't surface as many relevant candidates. And even if we look at pi uniform, which is the policy, so in taking stochasticity of rankings into consideration, the cost is even, it's lower, but still it's high, it's 0.75 for all the stakeholders. So we asked this question, if we could have best of both the worlds, if the cost can be evenly distributed and if the costs can also be as low as possible. So consider this alternate proposal where the first candidate is selected from the orange group, the second from the blue group, and the third again from the orange group. And again, the same thing, 3 qualified candidates in both groups. And now we look at the cost burden by the same definition. It's evenly distributed and it's lower than what we have seen so far. So just to recap, we saw PRP principle, most of the burden of the orange group, sigma uniform, 1 instance of uniform ranking, evenly but high, pi uniform, even, still high, and then sigma PR for the fair ranking. So we formalize this notion starting from the axiomatic fairness of uniform random lottery. And the axiom is that for 2 groups of candidates A and B, we say that a policy is equality of opportunity fair if it selects an expectation in equal fraction of relevant candidates for the top K subsets by K. But because ranking is inherently discrete, we have to we come up with this delta term and define the delta UR fair ranking so that the expected fraction of relevant candidates between the groups, it can vary by delta for any prefix K. So note that this is an non-amortized notion of fairness so that this fairness is satisfied at every prefix K of the ranking. And also we don't designate any group as the disadvantaged group, unlike affirmative action, demographic parity, and so on. So we leave the normative decision to the principal, basically. Yeah, the key point of our work is not to replace the human decision maker, but just to make them more effective by surfacing more candidates more relevant candidates in the top K. So the algorithm is simple, practical. We present this simple, practical, greedy algorithm, and the goal is to minimize this unfairness that I just went over, defined by this delta term, but at the same time select as many relevant candidates as possible. So the input is the PRP ranking for both the groups, and then the selection principle is to select the candidate whoever's, by adding to that prefix, whoever's delta comes out to be the minimum. And the runtime complexity is just n log n because of the sorting. We established 2 theorems in our paper, and these theorems are related to what is the global cost and fairness guarantee. So what is the cost optimality of such a greedy algorithm? Because you can imagine you could do the integer linear program, get the exact solution, but for larger rankings, it's going to become difficult. And so compared to the exact integer linear program formulation, we relax it to the LP. We use principles of duality to come up with the bound. And so the bound is pi delta max. It essentially depends on the specific, the expected posterior mean. And PAPB, they are the last elements that the EOR algorithm selected at the position K. So this cost is small. This cost optimality gap is small. For the empirical evaluation, we evaluated on the US Census Survey data set. This was a fairness benchmark data set released by Ding et al. In 2022. They essentially cleaned up the US Census Survey data set and added 2018 data. We evaluated for the state of New York, and we have individuals that belong to either white racial group membership or Black African American racial group membership. And we use the binary task of predicting whether the income of the individual is greater than 50K, which can then be used for ranking to, for example, provide loans to individuals. So this is the plot for the delta, the unfairness. And as we can see that PRP is deviates away from the line. So the 0 line is where you want to be for delta to be as low as possible. PRP is high, demographic parity is on the other side of it. We also benchmark against Thompson sampling policy, which was a method for ranking, fair ranking under uncertainty, which was introduced in 2021, but it doesn't take the group fairness into account. So it also deviates away. And then uniform and EOR, they're both close to 0. We also look at the cost distribution because our motivation has been looking under the lens of this cost burden for both the groups. So we have the total cost and the group A and group B cost, and you can see in PRP, all 3 are not the same line. So the x-axis is the length of the ranking. And for Thompson sampling, the gap is closer than PRP, but it's also not the same line. Demographic parity, it does not overlap. Uniform, all 3 lines overlap, but it is much higher. And then EOR is the blue, which is lower and also overlaps. All 3 lines overlap similar to uniform. We also audit a real-world data set of Amazon queries. The example is a bit nuanced, so we detail it in the paper, but we are auditing whether a given real-world data set presents fair ranking or not using the EOR criteria. So in summary, we highlight how disparate uncertainty between groups in machine learning models that can lead to unfairness in rankings. And then we present this fairness criteria, which we call equality of opportunity rankings, which is grounded in the axiomatic fairness of random lottery. I talked about the greedy algorithm and the even distribution of costs. But for future work, we're very excited to extend this to long term. So like in an online setting, so that it can incentivize the principle to reduce uncertainty for both the groups and surface relevant rankings. That's all. Questions?
Is there any question?
Yeah. I thought that was very interesting. I don't have any knowledge about fairness, so that was very informative to me. One question: when you say a candidate is relevant, in your example, you say that 3 are relevant. That's based on what? Because there's a predicted distribution per candidate, right? So what do you mean when a candidate was relevant?
Yeah, no, that's a good distinction. And actually I glossed over the details. So RI is the relevance. So in the model and the theorem that we're proving, we say that RI is distributed by some Bernoulli distribution. But like in real life settings, so for like the US Census Survey data set, we have true labels of the relevance of the candidate. So we evaluate by the true labels.
Are these binary labels or yours?
Yeah, they're binary. labels.
So you don't have a ground truth regression value for them. Rather than
So yeah, it's like we trained a gradient boosting classifier to predict whether the income. So the U.S. Census Survey data set, we predicted this classifier to predict whether the income was greater than 50K.
so these distributions are really unfairly flat or peaky. You can tell that because you have the ground truth labels for the candidates. Okay, that was a bit missing, I think, from the presentation.
Question. If not, then maybe we can say it. And then so the next speaker is Michele Capriel. That's correctly. He will talk about the knowledge-based theorem for upper probabilities.
Thank you very much to the organizers who gave me the opportunity to speak here. And yes, so I'm Michele. I'm presenting a novel-based theorem for upper probabilities. This is a joint work with Yusuf and our PIs, Aike Hülermeyer and Insuf Lee. It's a joint work between UPenn and in Munich. So the main motivation of this work is to pay homage to giants in statistics, Larry Wasserman and Jake Dane, and doing it in here at CMU is even cherry on top of the cake. The second motivation is to introduce an uncertainty-aware technique to be deployed in safety-critical applications, and we will have a very simple example in model predictive control. This uncertainty-aware technique is exactly this new Bayes theorem. So Bayes rule is arguably the most common updating rule for subjective beliefs. We all know this. And but what happens if the agent is not able to specify a single prior distribution, or if they face difficulties engaging the data generating process? In economics, this is called ambiguity. Ellsberg was the first one to study it, and then Gilboa and Marinacci more recently. And ambiguity is strictly related to the notion of epistemic uncertainty for ML and AI. And by now, you all know what the epistemic uncertainty is. So thank you also to Fabio today. So I can just gloss over this. Right. So this is a base for upper probability, Bayes theorem for upper probabilities. So some background on imprecise probabilities. An upper probability is the upper envelope of a set of probabilities. So this, I don't know if the supremum, thank you. Thank you. So it's the supremum over the set of probabilities. Okay, the lower probability is it's dual, so 1 minus the upper of the conjugate, so basically the infimum. And we say that the upper probability is concave or two alternating if the upper probability of the union plus, oh, by the way, this is a theory talk, so I apologize in advance. So if the upper probability of the union plus the upper probability of the intersection is upper bounded by the sum of the upper probabilities. This has a philosophical interpretation, but because it's not important for the sake of the talk, I won't give it to you.
Should that corresponds to the interval probability system?
Yes, definitely. Yes. And in the language of Robin Gong and Xiaoli Meng of their 2021 paper, we say that the upper probability is compatible with what we call the core. Again, I have a background in economics, so this is what economists call this set. It has other names. You will forgive me for my mistakes when I was younger. So the core of the upper probability is the set of all probabilities that are upper bounded, that are, set-wise dominated by the upper probability. Okay, so this is the definition, and the characterization basically tells you that it's the set of probabilities that are upper and lower bounded by the upper and lower probability. Nothing major. So it's easy to show that the core is convex, and throughout my talk, I will assume that it's non-empty because I want to use it. And it is closed in the weak star topology. And for those of you who are more mathy, the weak star topology is the coarsest topology that makes the elements of the dual continuous. Okay, nothing major. Now, by the way, if there are any questions, please interrupt me. I'm more than happy to take any questions. Now, an important example of a core is the so-called epsilon contaminated class, and you will see why this is so appealing. So it's very easy to specify. So basically, give me any probability, then the epsilon contaminated class is the class of all probabilities that can be built as follows: 1 minus epsilon times the probability that you want, plus epsilon times all the other ones. And I mean all the other ones. Here it could be, if P is continuous, this could even be discrete, whatever. It's really everything that you want. And why is this so cool? It's so cool because we have an expression for the upper probability, an explicit expression. We have one for the lower probability, and we know that it's actually a core. It's the core of the upper probability. And also, we know that it's concave. We have basically everything that we want to. Now, why did I introduce you this example? It's because we will use these epsilon contaminated classes when we apply to model predictive control later. Okay.
Did you get this from your visit to Taiwan?
Well, yes, but also I have been obsessed with this paper by Wasserman and Cadane since I was in my second year of master's. So this is really a thing that lived in my mind rent free for a while. So now, before I go on again, the idea here is to combine with a new rule the upper prior and the upper likelihood to obtain the upper posterior. Okay, this is the take home of the talk. But we have some assumptions on the way, right? So theta is the parameter space of interest, and we let the agent elicit, or before I go on, so I will now give a way of constructively come up with a set of priors and a set of likelihoods. But you're free to, the agent is free to sidestep this and directly go to the core as we will see later. But this is it's instructive because it is constructive somehow. So we let the agent elicit a set of probabilities, right? And this captures the ambiguity faced by the agent. So again, the epistemic uncertainty that we were talking about before. And also why we want to do this, because as Grunwald and Van Homen proved in 2017, Bayesian inference may suffer from inconsistency issues if it's carried out using a misspecified likelihood. So we may want to hedge against this problem by specifying more than one likelihood via this set L theta. Okay. We call L the densities of the elements of the set, and we assume that every density is bounded and non-negative. Now, this may sound like a strong assumption, and it kind of is. Two things I have to say about this. It's needed because I need upper Hemi continuity in the proof of the theorem, and also I feel in the future this will be, I don't want to say easy, but not too difficult to relax, thanks to the technique developed by Gerd de Koeman and Matthias Troffes that we heard earlier today. So I'm hopeful for the future. Now, For the set of priors, similarly, we let the agent specify a set of prior probabilities. And what we do, what they do is they represent their incomplete prior knowledge around the element of the sigma algebra in the state space. And this is the constructive the constructive approach that I was telling you about before. We compute the upper probability of this set and then consider the core of this upper probability. This represents the agent's initial beliefs, and it has mathematical and philosophical reasons for which we want to use the core. The mathematical one is the Gong and Meng, that is the compatibility, and philosophical reasons, basically, it's very profound, but it allows to overcome some of the critiques that have been moved towards classical Bayesian statistics.
So you're convexifying the set.
Look, you could actually, so all of this you could sidestep. You could just go ahead and specify the prior as the core of an upper probability if you were able to specify directly an upper probability. I'm just doing this for it to be more applicable somehow. So you come up with a set of priors, even finite, convex, whatever you want. Once you have it, compute the upper probability, and once you have the upper probability, you consider the core, and that's going to be your prior set. I want to work with the cores because that is going to give me some advantages to be able to compute the actual procedure. Sorry. Does that make sense?
So far, this is equivalent to a lower number probability system.
Exactly. That's yes.
The point is that it makes more sense to work with lower number probabilities than arbitrary sets.
Yes. Well, it makes more sense in the context of the theorem that I want to prove. Yes. To work with this core. I call it the core, but yes. And we do the same for the set of likelihoods to obtain L-co, right? I use this superscript co to highlight the fact that they're actually cores. Make sense? Now, this is, if there's one thing that you bring home from this talk, is exactly this picture. So what I want to do is to go from an upper prior and an upper likelihood and compute in just one operation the upper posterior. Okay, this is I would argue this is very interesting because this set right here has cardinality Aleph1, and this guy right here has cardinality Aleph1 as well. This guy right here has cardinality Aleph1 as well, right? So if we are able to actually compute the upper posterior just in one path, in one operation, we gain, well, a lot. Okay, so the main theorem then it's this one. It's a mouthful, but basically it says that if the prior set and the likelihood set are non-empty and weak start closed, then I can give you two bounds for the upper posterior. And then if the upper prior is concave, then these inequalities hold with inequality. Okay. So one more time, we start with an upper prior. We have an upper and a lower likelihood. Here, the lower likelihood is here in the numerators. And what we are able to do is, if nothing else holds, apart from this assumption right here, then this upper bounds are true. And if in addition the upper prior is concave or to alternating, then these are equalities, and we got the upper posterior in just one operation. And of course, the corollary is that, so this basically is a simple extension of Wasserman and Cadet's result. The proofs are also, the proof techniques are also kind of similar. And a lemma.
Right, I remember that paper. So Wasserman was doing this sort of robust based theorem.
Look, he had it.
So the difference was that he was only considering one
likelihood. Yes.
Instead of a convex set of
Exactly.
So you're extending this, not just a convex set of prior.
Yes. And I did that not only because I like it, but because we had this model predictive control application in mind, and it's the next slide. Okay. Another lemma that we were able to find was that if the upper prior is concave, so will be the upper posterior. And this is nice because it means that I can use this result in a subsequent fashion, right? Because if you can remember, if the prior was concave, then these two are equalities. So if I have an upper prior, my upper posterior will be concave as well. The upper posterior becomes the upper prior at time t+1, and so on and so forth.
So in other words, this is closed in the space of nowhere.
For concavity, yes. Okay. So how am I going to apply? Very quickly, the application. So the application is the following. So model predictive control, I trust most of you know what it is, but it's a method that is used to control a process while satisfying a set of constraints. And typically when the process is stable, what Bayesian statisticians do is to specify a normal likelihood centered at the objective function of the process and a normal prior on the parameters of such function. But two things. If ambiguity enters the picture, then our results become relevant. Why? Because first of all, we may run into inconsistency issues, as we said before, if the likelihood is misspecified. But more importantly, a precise normal likelihood is a good choice only if stability of the process is ensured. So if sudden shocks may happen, we may want to take that into account by specifying a set of likelihoods. So what the practitioner could do is to specify a set of epsilon contaminated truncated normal priors and a class of eta contaminated truncated normal likelihoods, and then use our theorem to compute the posterior. Why truncated here? Because again, I had that assumption at the beginning that I needed the distributions to be bound. Right, so I don't have a conclusion slides, but I can tell you out loud. So what's next? So again, the main take home is that picture that we saw before. And for the future, the idea is to, first of all, try to let go of the assumption. And second, to actually implement it. This was, let's say, a direction, like a more pointing in the direction that we want to go. We would like actually to implement it in an MPC serious application, so that we can actually let people apply it. So thank you for your attention. Here you can find the paper. And just one extra minute. If you're interested in precise probabilities, you can join CIPTA, or if you're not ready to join it, there's going to be a summer school next year in lovely Ghent, Belgium, where you can learn about the precise probabilities. Thank you very much.
Any questions?
Yes.
Thanks for the talk. I have a question more about sort of the intuition about when like the Bayesian approach can go wrong and how that's different. So what does it look like for a likelihood to be misspecified? And is the approach you're taking somehow analogous to having maybe a family of priors? There's hybrid prior perhaps in your prior, or is that
So there are two questions, right? So the first is the misspecification of the likelihood. I don't have a good answer because that's not my area of research. I suspect that many of the Bernstein von Mises guarantees would fail to hold when the likelihood is misspecified. So that is the short answer. The long answer is I don't know better. For the prior, can you repeat for the prior?
So
You can use a hierarchical prior.
Yes. Okay, in that case, we would be something like a second order distribution, right? Yeah. So in that case, there is a nice paper from 2022 by Victor Banks at the LMU, where they show that second order distributions are kind of suboptimal to gauge epistemic uncertainty. So if you have the chance to do it, you should go create sets. So that's why we decided to go with that.
I have a follow-up on what you just said. I was going to ask you if you thought of working on Bayesian for Mises like guarantees for critical updates of this kind? Because this is the main weak spot of Bayesian reasoning, right? So I think could produce a theory of robust Bayesian reasoning based on credo sets that has Bayesian premises like guarantee.
My money would be on the fact that some people already worked on that. I'm thinking of Gert's group in Belgium.
Maybe, but I'm not really.
Yeah, no, me neither. But that's certainly something that's worth exploring in the future. Yes. I think there's another question.
Does the upper posterior behave like a distribution? Like, does it make sense to take a map estimate or?
Oh, the upper posterior is sub-additive. So you use additivity. Actually, with you know this, with all the upper bounds become sub-additive and the lower bounds are super-additive. So you would have, for example, that if I have imagine that omega can be partitioned into A and B, you have that P of upper posterior of A plus upper posterior of B is not necessarily one, it's modular equivalent, something like that. Thank you very much.
I have one more.
Yeah, sure.
How do you choose epsilon?
Oh, that's new. That's so new, and I think it has to do with the fact that at the end of the day, Bayes is still somehow rooted in subjective statistics, or it reflects your subjective beliefs, right? In some sense. So the idea would be that you would choose epsilon larger for a higher degree of perturbation, whereas if a smaller degree of perturbation is enough, you would set it close to zero.
Okay. And what if your second term, which you say everything else, the first term was your prior, you can use like how you mentioned, but something from imprecise model like interval.
So you want to.
And that makes sense to take care of the epistemic uncertainty. So the first part takes the electric, is your prior distribution, and the second one, like the interval, which is basically MPC called model predictive.
Okay, I haven't thought of that. So I'll tell you, I'll give you an answer. So when you have sets like that, what usually people do for aleatoric and epistemic uncertainty would be either to consider upper and lower entropy, right? So the lower entropy would be the aleatoric uncertainty. The difference between upper and lower would be the epistemic, and the upper would be the total. Or you could use the generalized Hartley measure, which needs a Moebius kind of representation, and therefore it's harder to compute, but it doesn't have the shortcomings that yeah. So I haven't thought of actually combining a set with a single distribution. But that's interesting. I should thought.
Have you applied to MPC any tests?
So I have an application that we didn't put on the paper because it was again a theoretical application. We didn't have any experiments, and that's why it's still in becoming somehow.
Thank you.
Thank you very much.
Okay, very good. So our next speaker is Aditya, which he will give our last keynote speaker about distribution-free uncertainty quantification for black box machine learning prediction methods under distribution theory and scholarships. Please, Aditya.
Great. Thank you very much. Hopefully you can hear me. Starting at around 5:10, so hopefully ending closer to 5:40. Okay, so there's three pieces of the title that are going to be relevant. what does it mean to quantify uncertainty without making distribution assumptions or distribution-free uncertainty quantification? What does that mean? Black box machine learning prediction methods, hopefully you have an idea. Essentially, we're not going to make any assumptions on the underlying machine learning methods used. And the last part is we want things to hold when the distribution is drifting or shifting. That's going to be the key innovation. The past work is essentially going to be things that work in IID setups, but we want to extend things to work with changing, shifting distributions. Okay, so here's a rough talk outline. I'll be talking about two settings for distribution-free UQ, and the first one is prediction sets, and that's captured by conformal prediction. The second one is calibrated probabilities for classifiers, and there I'll be talking about post hoc recalibration. So two different notions of uncertainty quantification, two different ways in which they're going to be distribution free. And so I'll just introduce those settings, but those will be, for the IID setup, that's past work. And I'll tell you about new algorithms that came out this year, that were published this year. The first one is called non-exchangeable conformal prediction. It extends and generalizes conformal prediction, and it guarantees to hold for settings beyond exchangeability. And the second one is something called online flat scaling, which is an online recalibration method that works even if distributions drifting and shifting. Okay, so that's the rough outline for the talk today. Okay, so here's a brief recap of the problem setups in the IID world. So what we're going to do is we're just going to define some goals of what standard, by standard I just mean in the IID setting, distribution-free uncertainty quantification is. So what are the goals? So I think of things in terms of being a pyramid. So there's a little bit of a lag between when I change the slide and when it appears over there, but hopefully we'll get over that. I think of things as being a pyramid. There's three notions of uncertainty quantification that you could be interested in, like in a prediction problem. So you have features X, you have outcomes Y, you want to quantify your uncertainty. So the first one, I'll be talking about two of them. So prediction sets is I'm trying to capture for a new test point xn plus 1, I'm trying to come up with a set which captures the unknown observation yn plus 1 with some pre-specified probability. So it's not a confidence set, it's called a prediction set. Another notion is what's called calibration. This would make sense in multi-class or binary classification settings. I'll define it again properly later. And the last notion I won't really talk about, but in this NeurIPS paper, we show how these three notions are related to each other. It's about confidence intervals, but confidence intervals for what quantity are you covering? A natural quantity to cover, for example, is the regression function. Turns out to be a hard problem, but we can relate all three notions. And this talk will be about prediction sets and calibration. Okay, so they're related, but they're completely distinct notions. Okay, so here's what predict, the difference between prediction and predictive inference. Okay, so in prediction, we have some training data. This is the bag of training data. We get the n plus first point. We want to predict the last point. So what we do is we come up with some algorithm. The algorithm takes in training data and outputs a predictor. A predictor is just some mapping from script X to script Y. And what's an algorithm? It's just any function that maps some amount of training data to a predictor. Okay, so you use your favorite algorithm, you have a predictor, and you use your predictor to say, well, my guess is a of xn plus 1. That's what all of machine learning does. But what we want to do is what it's called predictive inference. And so that's where we are quantifying uncertainty. We don't want to just give a point prediction. We want to give a set prediction. And we would like to come up with a set. I'm going to call that set Cn, because it depends on the first 10 data points that you've seen. And of course, it's a function of the n plus first point. So on seeing the n plus first point, you want to come up with a set such that the unknown y lies in that set with probability at least 1 minus alpha. So that's the goal of a prediction set. And the key part that makes all of this distribution free. So the goal of distribution free UQ means I would like this error guarantee to hold for all joint distributions PXY and all algorithms scripted, doesn't matter what algorithm you use for this prediction problem. I would like you to be able to construct such sets so that this guarantee holds for all P and for all A. And the usual setup is IID. So the only assumption is I have n plus 1, usually exchangeable, but you can keep it simple and think of n plus 1 IID draws from PXY. I don't know anything else about PXY. I don't know anything about that joint distribution. It could be heavy tail. It could be discrete continuous. I have no idea. And so I don't make any assumptions about it. And I would like, nevertheless, to have a finite sample guarantee of coverage of this unknown Y regardless of that. So that's the goal of distribution free predictive inference. And so if you haven't seen it before, here's like a one slide, hopefully 1 minute. I don't want to spend too much time on it, but it's a classic method called, there's many versions of conformal prediction. This one is called split or inductive conformal prediction. You have your training data. This goes back to Vogue and collaborators' work for more than 20 years ago. So you have your training data, you kind of split it into two parts, D1 and D2, and this is not an equal split. You should think about using most of your data in D1 and leaving a little bit of data aside for D2. You use the first part of your training data to actually run your machine learning model, and you come up with your predictor A. And what you do with the second part of the data is you calculate held out scores. So this almost seems like standard machine learning. You have held out data, you calculate some kind of loss of your algorithm A on your held out data points. So, RA of xi, yi, you calculate all of these scores for the points in the second data set. Okay, and now how do you summarize all of that? You summarize it by one number, a quantile, the 1 minus alpha quantile of these residuals. So you should think of these residuals as just being out of sample losses. So just larger losses, you're doing worse at prediction, and also called a non-conformity score. And so if your alpha is 0.05 and you have 100 elements kept aside in D2, then you look at the 95th element and you say, well, that's the 95% quantile of my held out residuals. And essentially what this number is telling you is how well am I doing out of sample? How well is this algorithm doing on points that it has not seen so far? And now you put those two together, the conformal prediction set, when you see a new point, xn plus 1, that's not over here, what you do is you keep the set of all y for which the residual of xn plus 1, when I plug in y, this residual is just a function that takes in two arguments, right? So you put in all y's and you see which y's give you a smaller value than this 1 minus alpha quantile. So these y's are going to be the plausible y's. They have a relatively small loss. And it turns out that if I define my set in this fashion, then I get non-asymptotic, completely distribution-free control. So like the probability that yn plus 1, the thing I don't know and I want to cover, actually lies in this set is at least 1 minus alpha. And it's not too loose. I mean, I'm looking for 95%. I also get close to 95% where N2 is actually the size of D2. So basically get 95%. So, okay, so that's, the usual split conformal prediction. The proof is 2 lines long and it works when your data is IIT or exchangeable. Okay, so that's just background. The second notion I want to tackle today is calibration. So what is calibration? Here you should think about binary classifiers. All of this will work even if you have real valued outputs, even if you have multi-class classifiers, but keeping it binary is easier for a talk. So if I have a binary classifier, it returns a probability. It's supposed to try to return a probability. I'm going to call that classifier calibrated if the expected value of yn plus 1, given what I output f of xn plus 1, actually equals f of xn plus 1. Okay, so if you've seen this before, it's a very obvious statement. If you have not seen it before, it looks mysterious. So here's the rough intuition. The idea is if we predict f of x as 0.3 for many different points, I would like about 30% of them to be ones. If I predict f of x to be 0.5 for a set of points, I would like about half of them to be ones. And so essentially that's captured by this definition of calibration. So when I predict f of xn plus 1, I would like my expected value of y to actually be f of xn plus 1. Now, in reality, exact calibration is essentially impossible with a finite data set of size n. And none of our trained classifiers that we use are automatically calibrated. In fact, they can be quite miscalibrated. So what we want to do is post hoc calibration, which is we have trained our classifier, our deep net or random forest or whatever it is that we like. We want to post hoc calibrate it. And a post hoc calibrator is just a function that takes in an initial classifier, I'm still calling that A, and kind of a small calibration data set that you've kept aside, and now output something that hopefully is calibrated afterwards, but it will not be exactly calibrated, it will be approximately calibrated. So you want to take in a classifier, calibration data set, output an approximately calibrated classifier. How do I quantify approximately calibrated? If you've heard of PAC in PAC learning or PAC base, this is also PAC, except it's probably approximately calibrated. So we say that this method is some method, and we have to design such a method, but the method B is going to be distribution-free epsilon alpha calibrated if the error, I would like this difference to be 0, but if it's not 0, but the probability that it's greater than epsilon is at most alpha, and hopefully epsilon alpha is small, then I'm going to call it epsilon alpha calibrated. And ideally, when as n goes to infinity, as I get more samples, I would like epsilon alpha to go to 0, and in that case, I'll call it distribution-free asymptotically calibrated. The distribution-free part again over here is I would like this guarantee to hold. I want to design methods P such that this guarantee holds no matter the distribution P that I have, like over X. In this case, it's a binary problem, so Y is just 0, 1. But no matter what the distribution over X is or what the joint distribution is, it shouldn't matter at all. So that's the goal of distribution-free calibration. And because I introduced split calibration, a simple idea for calibration is what I'm going to call split binning. So you take your training data, you split it into 2 parts. Again, you want to keep this part much larger than this part. You use D1 to actually train your classifier. So you get a classifier A, it's not actually calibrated. And then what you do on your second half of your data, maybe only 100 points or something of that kind, you split it into bins. In this case, I'm going to just show you 2 bins, but typically maybe you would pick 10 bins or something of that kind. And you should think of the bins as being the held out points for which my classifier thinks the probability is of label 1 is less than 0.5, and the held out points for which my classifier thinks that the probability is greater than 0.5. So I kind of split this second data set into 2 bins, the less likely points and the more likely points, but less likely or more likely according to this A. And then what I do when I see a new point xn plus 1 is the following. Like let's say that A of xn plus 1 is 0.3. I don't output 0.3. I say 0.3 corresponds to the first bin. And instead, what I'm going to output is the average of the y's in that first bin. So I have a bunch of points in that first bin, which are from D2, and they have some actual true labels y, and I output the average of those y. So maybe that comes out to 0.4, and maybe I'll output 0.4 again. And so similarly, if A of xn plus 1 was 0.8, I don't output 0.8. I say 0.8 actually is in the second bin. And what I'm actually going to output, the recalibration, is instead of saying 0.8, I'll output the average of the y's in the second bin. So it's a very simple idea.
Discarding the score.
No, I'm not. I'm using the score of the classifier as a mapping to the bin. But in this case, it's
specific data point. You're discarding the score for specific data. So just referring to scores for your.
Yeah, I use the score to find out which bin I should look at. So if my A of xn plus 1, my score was 0.3,
it's clear, but it's
a
unique relationship between what you output and
yeah, it's not a unique relationship. That's right. Yeah. And in fact, we prove in this paper that that if you have a one-to-one relationship between the scores and your recalibration, if you have one-to-one relationship, then you can provably not be distribution-free calibrated. So we actually have an impossibility result in the paper that says effectively that some sort of binning is necessary for distribution-free calibration. And for this particular one, you get a simple bound that says, on my new point xn plus 1, the difference that I would like to be small, the probability that it's actually larger than a shrinking quantity is less than alpha. So this results from some kind of simple concentration inequalities. I'm only showing it to show you that you do get distribution-free calibration from this kind of simple method. But in practice, you don't want to do something so simple. It's just easy to show in a talk that distribution-free calibration is achievable by some simple ideas. Okay, so and again, this guarantee that you finally get does not make any assumptions on the underlying distribution or on the underlying algorithm. Now, so that's like, these are ideas that are old. Like, these are totally not new ideas. People have been using binning for recalibration for decades, and people have been doing conformal prediction also for 2 decades at least. And so what is going to be new is how to move these ideas beyond the IID setting. So all of the guarantees and algorithms typically work well in the IID setting. How do we move beyond that? Okay, so we immediately hit an impasse. We asked, well, when we move beyond IID, that's a crazy and rich world. Like, if my data is not IID, I have suddenly no control of it. What am I actually even aiming for? What's the goal? So here's the rough goal. What I want is that if the data distribution drifts and shifts over time in some manner that I don't know in advance and I will not assume anything about, I would like to still ensure that my coverage is good or my calibration guarantees are good. And we'll see later what we mean by good. What we would like something like some kind of a smooth degradation in the sense that if I have an adversary creating data at each step, there's almost nothing I might be able to do. But if my data distribution is drifting gently or smoothly over time, I would like to get pretty much exact coverage or calibration regardless. So I would kind of adapt somehow to the difficulty of the problem. And of course, harder problems I'll be able to adapt worse, but I want to have non-trivial mathematical guarantees for these algorithms across situations. I also don't want to hurt myself in the IID setting. I have things that work well if the data is IID. What I would like is that if the data happens to be IID, then the algorithms and the guarantees should somehow be identical to the previous papers that assume the IID case. So I don't lose robustness to the IID case. If things are IID, I get exact coverage, I get calibration as I had before. But if things are not IID, I would like some attempt to adapt to it. And so, yeah, I'll give you, we want algorithms that adapt to changing distribution, but don't hurt you when the distribution actually doesn't change. So the setup is going to be one of a sequential setup. So at each time t, we're going to observe some features xt, and depending on the problem, whether we're trying to output calibrated probabilities or we're trying to capture y in a prediction set, depending on the problem setup, we'll output some ct or calibrated probability pt, and this step is going to use some arbitrary machine learning model, some regression algorithm or some classification algorithm as guidance. And then we'll observe the outcome yt, and this game keeps going on forever. And the desire, as I said before, was some kind of adaptive behavior to the changing distribution of xt and yt. Okay, and so we're not going to assume IID anymore. Okay, so the first paper that I'll try to summarize in the next 5-10 minutes is titled Conformal Prediction Beyond Exchangeability. It just appeared a couple of months ago in the Annals of Statistics, and it's joint work with excellent co-authors of mine, Lina Barber, Emmanuel Candes, and Brian Tipshirani. So here, I'll try and get right into it. So I've introduced conformal prediction. It's very simple. You have to choose a conformity score, and then the algorithm is really quite simple. So when we move to the non-exchangeable setting, we need two more notions. Okay, so these notions are weights and tags. They're both very simple. I'll tell you what they are. So what's going to happen is that every point is going to be assigned a weight in 0 to 1. And the last point has a weight of 1. These weights are not likelihood ratios or importance weights or anything of that kind. There's no assumptions on these weights. We'll have a theorem that whatever the weights are, we'll write down a theorem for them. But roughly, you should think about these as, for example, if I actually am in a temporal setting, then I want high weights for recent points and low weights for old points. They're roughly going to be which are the points that are relevant to predicting the current one. So you can use your prior knowledge to come up with these weights, or you can just assign a decreasing sequence over time if you have no prior knowledge. And so W tilde I is just going to be a normalization of these weights. So that's some additional thing. So not only do I have Xi and Yi, I also have these Wi's that you choose. This is user chosen. And every point is also assigned a tag. A tag is simply because we often use algorithms that treat points symmetrically. Like if I throw data into a random forest, it actually doesn't matter which point was labeled 1 and which point was labeled 5. It just treats it like a bag of points. And so this tag exists just so that the algorithm can actually distinguish between points. And so the tag could be the time at which you saw that point, or the some kind of index of the point, or a spatial location at which you collected that point, or something else that uniquely identifies that point. If you don't want to use the tag, you don't have to, then the algorithm will reduce to the exchangeable case. So essentially, if you want to use asymmetric algorithms, then you put the same tag for everybody. But if you want to use an asymmetric algorithm that treats different points differently, then this tag, it allows you to use asymmetric algorithms. This is just it's a feature that you can choose not to use if you don't want to use it. Okay, so here is the algorithm. So I'm going to describe, even though I presented earlier split conformal prediction, there are many variants. There's something called leave one out jackknife plus, there's cross conformal, there's full conformal, and things of that kind. And so here, just to be slightly different, I'm going to present the non-exchangeable version of what's called full conformal prediction, in the hope that some people have seen conformal prediction before, so this won't be entirely new, but it'll be similar in flavor to the earlier algorithm, but a little subtlety in how do I use the weights and tags. So here's the summary is, all I'm going to do is I'm going to use a random tag swap at one step. And then instead of using a residual distribution and looking at a quantile, I'm going to look at a weighted residual distribution and look at a quantile. Okay, so here's the method. I'm going to pretend that the last data point, whose y value I don't know, is actually just xn plus 1 and little y for some hypothetical little y. And I'm going to pick a random index k with these probabilities w tilde I. This is where one place that the weights are coming in. So essentially from 1 to n plus 1, I pick a random index k. Okay, and so if my weights are decreasing, then this index is more likely close to n plus 1 and less likely to be a small index. And then I'm going to do a random tag swap. So I'm going to essentially apply my training or machine learning algorithm, but to a slightly different data set. It's to a data set in which I give the kth point the n plus first tag, and I give the n plus first point the kth tag, and the rest of the data remains untouched. So it's an interesting twist, and maybe I can discuss offline later why you need this twist, but you do need this twist. And so this is where you just apply conformal prediction, and the tags are swapped. But if all the tags are identical, then this step doesn't do anything. It doesn't matter if the tags are identical. It's only to cover asymmetric algorithms. So the third step is calculate residuals as you did, standard conformal prediction. You calculate the residuals on your data points, and then you keep the set of all y's for which the n plus first residual is less than the 1 minus alpha quantile of now the weighted empirical distribution of the residual. So earlier, all the weights for 1, you recover the earlier thing when I said if all the weights for 1, it's just the 1 minus alpha quantile of the residuals. But now I had some weights, so this is a weighted residual. Okay, so except for this kind of tag swap and these weights, this is actually, looks a lot like what conformal prediction is doing anyway. Now, the one part I didn't emphasize as much earlier is conformal prediction needs two assumptions: that the algorithm is symmetric and that the data is exchangeable. And this will relax both of them. You're allowed to use asymmetric algorithms, and the data does not need to be exchangeable. So let's look at the theorem that we prove. So this is what the theorem looks like. Okay, so the theorem makes no assumptions now on the data or the algorithm, which means no exchangeability and no symmetry, nothing. So this is an assumptionless theorem. And our algorithm, non-exchangeable conformal prediction, satisfies these upper and lower bounds. I'll not, it's like you have an upper and lower bound for conformal prediction of coverage. I'll just ignore this upper bound. It's the lower bound that's interesting. We were targeting 1 minus alpha coverage. What you do get actually is 1 minus alpha minus, you should think of this term as some kind of price of deviating from exchangeability. So it's like capture some kind of non-exchangeability of the data. And so what are these terms? So this is the weights that we had before. Remember, they sum to 1. So this is a convex combination. And this is the total variation distance between the residual vector of my original data, the original full data set, assuming yn plus 1 is also in there, and the residual distribution of the data with the ith point swapped with the n plus first point. So those two residuals. So if the data is not exchangeable, this is actually not non-zero. But if the data is exchangeable, then swapping 2 points doesn't change the distribution. So this is actually equal to 0. So this is one example of what I meant by if the data was exchangeable, this is 1 minus alpha. There's no problem. Even though we used weights, even though we used an asymmetric algorithm. So actually, this algorithm generalizes conformal prediction to allow you to use asymmetric algorithms. And when your data is exchangeable, you'll still get 1 minus alpha coverage. But you need to do that random tag swap. Otherwise, standard conformal prediction with an asymmetric algorithm does not have 1 minus alpha coverage. Okay, and so many interesting things to say about it. A few kind of remarks are, if you have identical tags, it reduces to a symmetric algorithm. If you have identical tags and equal weights, you just recover the classical conformal prediction algorithm. And our theorem then tells us, how does classical conformal prediction do if we use weighted residuals? How, does it have any coverage guarantee? And the answer is yes. In fact, the data is exchangeable. The use of weights does not affect coverage. And if you use equal tags and weights, how does classical conformal prediction do without any assumptions on the data? It tells you exactly what the loss in coverage is going to be. If you have exchangeable data, there's no loss in coverage. If you have distribution drift, then what you want to do is pick weights which are, one is the last point, and then you have a decreasing set of weights. And the reason is that, well, I mean, if you go back to the theorem statement, what you expect over here is that the nth point is very similar to the n plus first point. So this total variation distance will be small, but I gave that a very large weight. So very small total variation distances had a very large weight, but maybe the first point is very different from the n plus first point. So this total variation distance is large, but I gave that a very small weight. And so essentially the loss in coverage will be very small. So it gives you guidance for what you want to do if your distribution is drifting. And the last important point is actually the total variation distance between the data doesn't matter, only between the actual residual distribution. So for example, if the distribution shifts in irrelevant features, and let's say you're running the lasso and the distribution was drifting in irrelevant features, and the algorithm ignores those features anyway, then there's no loss in coverage. So I mean, that's kind of a trivial analysis would give you this kind of a term and not this kind of a term. So the analysis is actually involved. Okay, so how am I doing on time? A few minutes left. Yeah. So I'll give you an example of how this does on electricity forecasting. So this is data from New South Wales and Victoria in Australia. Here, there's electricity usage priced every 30 minutes. I have covariates X, which are the demand in New South Wales and Victoria, and the price in New South Wales and Victoria. And the response is the electricity transferred between New South Wales and Victoria. So this is a very non-stationary problem. I mean, at every half an hour interval, there's all of these are drifting distributions. But I'm trying to predict how much electricity is going to be transferred between those two states. And so at each t, we produce a prediction interval for yt, and then we actually observe the yt and so on. So here's a graph, and maybe I'll end on this graph. I have here the coverage against time, and maybe the thing to notice effectively is that if you use just conformal prediction, the coverage varies wildly. It can drop to as low as 60%. It can go up as high as almost 1. Just it has no control essentially on this kind of data. But by using non-exchangeable conformal prediction, we have much tighter control around the desired 95%. I mean, there are going to be some blips because we're making no distribution assumptions, but it's pretty good. And we don't suffer in the width. So if you look at the non-exchangeable conformal prediction, there's a place where conformal prediction drops in coverage. It's too short there. The non-exchangeable one gains by coverage by making it longer. But when the data is simple, it keeps the same coverage, but with much shorter interval. So it's not doing something trivial in some sense. Okay, so I'm reaching the end of my talk. So let me just tell you that if you look at the paper, we have simulations for change points and distribution drifts and so on, which you can look at, which I think are interesting and show the same thing, that somehow the desired coverage is really maintained at the level that we wanted. And we also had an example of election forecasting, where earlier in the night you observe results from the eastern part of the United States, and you want prediction intervals for the change in votes from 2016 in the rest of the United States, and how to kind of use conformal prediction method, but with distribution shifts and drifts to this kind of setup. Okay, so I don't have time to describe the second one. It was just presented last week at ICML. It's an online recalibration method. So we call it online flat scaling. But essentially, like the same, what we did for conformal prediction, it was to produce prediction sets. We now say, well, can we do a similar sort of thing, but for calibration, to produce calibrated probabilities? So we take in a classifier, but as the data comes in over time, we recalibrate this classifier. And so we call that online flat scaling. Flat scaling is a very classic method for recalibration in the IID setting. And online flat scaling is an online extension of that method that adjusts really nicely to distribution drifts and shifts. And calibrating is the notion of how to protect yourself against an adversarial nature at the same time. So somehow, if nature is nice, then online flat scaling works well. But if nature is adversarial, then this notion of calibrating protects. So in the interest of time, I'm not really going to have time to to tell you about this, but some very simple simulations in the paper suggest that this actually does really work well out of the box. So let me end by saying that I actually think that imprecise probabilities are really important and useful for machine learning, and somehow capturing epistemic uncertainty is critical. What we need are frameworks that are both computationally tractable as well as statistically meaningful. And hopefully the types of guarantees that we get out of these frameworks are interpretable. I've given you two examples of those frameworks. So the non-exchangeable conformal prediction framework is one of them, and online recalibration is another one. But I think I also work on game theoretic statistics, and I think that area also provides some interesting directions for capturing uncertainty in an interpretable and yet formal way. With that, I'd like to thank you and maybe take questions. Thank you.
Any questions?
I know, I would say. Very far.
Thank you for the talk. Is there a way of optimally choosing the weights? So I get you can't measure the total variation distance in practice. So is there an optimal solution to this problem, or a heuristic that seems to work well?
Yeah, there is a heuristic. If you have older data, you can affect, and if you have a reasonable model for that data. So, for example, if you think if you're willing to model your data in a way that you can at least upper bound the total variation distance, solving for the optimal set of weights on past data is actually just a convex optimization problem. The weights have to sum to 1, and they're positive and they sum to 1. And you're optimizing, you're just saying minimize the sum of weighted something subject to some constraint. And so at least, for example, if you had a Gaussian linear model for your data, you'll at least get a heuristic sense of how should I be rescaling my weights? What's a good way of decreasing my weights fast? So that is totally doable, and so we have run simple simulations to show that it does get something non-trivial. Sometimes you get polynomial or exponential decreases, and sometimes it says like do something flat, like weight all the last 100 weights the same, and then decrease your weights. And so you get different answers depending on how your previous distribution has been different.
Okay, great. Thank you.
Yeah, no problem.
Any other question?
I don't think this works.
No, that's no. So there's a lot of work in online learning, continual learning, on complex optimization. So are you working on the relationship between what you do and all this stuff?
Yeah. So that's a great question. Online learning as a field tries to minimize regret. Regret by itself doesn't capture any notion of uncertainty. But it turns out that both in the field of game theoretic probability and statistics and in online calibration, regret guarantees can be translated into the types of guarantees we want. So in fact, online plan scaling is actually based on running online logistic regression for the plan scaling parameters. And the regret guarantee you get actually then implies a bound on sharpness and calibration errors. And so, yeah, so there is a relationship, but somehow you have to translate regret bounds, which are really just losses, sums of losses, into uncertainty quantification of the style that we want. Yeah, so that's the answer. Yeah.
Any other questions? Otherwise, we can thank the speaker again. Thank you very much. So we are close to the end of the day, and we did leave some space for a panel discussion on the state of uncertainty quantification ML. Unfortunately, I invite the speakers not here physically today, but I think it's in a little bit of a attempt to have some conclusions on what we learned today would be in place. I think it's fair to say there's growing interest in uncertainty quantification and artificial intelligence. This is why there's quite a lot of people here today, and we got a pretty good number of papers submitted to this workshop. The other point I'd like to make is that probably the field is a bit composite in a sense. There's a lot of different approaches around, and it doesn't really. So different strands, they are not very much aware of each other, and they continue working in the direction without really a lot of exchange of information and the likes of reputation, or prediction, that people like us are trying to use higher-order probabilities, but there isn't really a lot of communication among all these different groups, which I think it's a problem. I mean, anybody feels like we're converging towards better understanding of how uncertainty affects machine learning, or you feel like we're still very far away from uncertainty? I mean, obviously we got a lot of results and even theoretical guarantees, but do we feel like we are really cracking, I mean, getting closer to cracking the problem, or getting a satisfactory answer to these questions, or not so much? I mean, personally, that's my question. I feel there's still a lot to do, especially in areas like continuous learning and online learning, where, only now people are starting to relax assumptions like IID, and which don't make any sense in the real world, to be honest. Because any problem you can think of. So basically, all that's been done in machine learning in the past 50 years is pretty much useless. Yeah, this is one of the things that we're trying to do with some groups in the Netherlands, in Oxford. Something similar to what you just showed. So extending uncertainty classification to continual learning, from our point of view, also. But also coming up with a conformal learning like framework that uses higher order probabilities and standard probabilities, and similarly pack-like guarantees that don't necessarily use classical probabilities. Just an example. Anybody has anything to say about what we heard today and what you feel the status of the field is? Or you're just too tired, want to go home? That's understandable.
I mean, maybe it's just a personal thing, but I like benchmarks. And it would be nice, for example, conformal prediction people are always on these coverage benchmarks that they do, where you cannot evaluate a traditional probability estimate or a Bayesian estimate. For me, like, the problem is more like representing the uncertainty, and the approach is, I don't care. Like, I don't care if it's Bayesian or conformal or traditional or pragmatist. It would be cool to have a benchmark, and then we can just try out what works best.
That's a very good point, actually. This is something we are trying to do within this project. We are trying to come up with a general framework for evaluation of uncertainty-aware predictions, which is not quite there. Even Bayesian paper, they tend to evaluate their performance just using classical metrics, and they put uncertainty on the side, sort of. Yeah, these are predictions. This is accuracy or whatever. Yeah, so by the way, these are the covariances, the entropy and stuff, but the measure of uncertainty is not incorporated in the evaluation, arguably, at least. So there's definitely a need for a comprehensive setting for evaluation of uncertainty with machine learning and benchmarking, because right now, if you do OOD, then you end up using like rotated MNIST or noisy MNIST or these kind of toy data sets that not really represent the real challenges that you encounter in the real world, like distribution shifts and the like. So I think it's a very good point. So benchmarking evaluation is definitely quite open area for investigation in my mind.
Hello, can you hear me?
Yes.
Can I ask you a question?
Yeah, go ahead. Who is speaking?
QJ, yeah. Online. Can you hear me?
Yes, we hear you. Could you please
introduce? Yeah. So my question is, what do you think of you apply uncertainty quantification to address the hallucination problem with large language model?
That's, I think, yeah, it's a not a very good point. So I just put in an ERC grant application a couple of months ago, and one of the points I was trying to make now is that language models, I mean, if language models were more aware of uncertainty, they would be less prone to hallucination, or at least more cautious in their statements and what they output. You know,
because when the large
two things are linked, the two things are linked. So the fact that these models are prone to hallucination and incorrect statements is linked to the fact they do not acknowledge their own uncertainty in making predictions. So I think you have a point there.
Because when a model hallucinates, it means it's not sure. It should be right. It means its output is not consistent with the training data. So I would think epistemic uncertainty probably can be used to detect.
Quite the opposite. I think the problem is that they are too sure of something that is not true. And that's because they cannot accurately quantify how uncertain they are. It has to do with calibration. That means, okay, it's a calibration problem, I suppose. So I think there's interesting work to be done there in relation between hallucination and calibration. Do you agree?
Absolutely, and I know that there is ongoing work on that. Yeah, I don't think, I'm not sure if you can hear me online, but I'm aware of, I met people at ICML that I know in the calibration area that are thinking actively about calibration for large language models. So, yeah.
Okay, thank you.
Bruce?
Maybe a quick follow-up. Oh, yeah. Maybe just a nice starting point would be the Anthropic paper from last December that also Yarigal mentioned. LLMs mostly know what they don't know. They try out different uncertainty methods to get hallucinations done over with. So it's currently being worked at. I guess that's a nice starting point if you want to get to the topic.
Good suggestion, yes. I don't really like the expression foundation models, to be honest. Now it's in the mainstream, so can't do anything about it. Left side of the room. You still with us? Oh, yeah, there's one there. Sorry, I'll leave you this.
Thank you.
You can go, please.
Yeah. Yeah, so besides like language, like sort of like a practitioner's question here is, we're working so hard to quantify uncertainty, which, you know, outside of some narrow mathematical sense anyway, ill-defined. So the question they ask is, what are sorts of application areas that where is there some theory to be done even into understand how to use uncertainty in an appropriate way, given that we can obtain it?
Yeah, I think this is strong. I think there is, and I think autonomous driving is a good example of that kind of application area, where in the end, you have to make a decision. You need to act as a mobile robot, and your decision needs to depend on this level of uncertainty, right? So that, I think, is a very clear example of a situation in which how you model and quantify uncertainty has direct consequences on how an autonomous robot interacts with the real world, right? And I don't think there is anything qualified there yet. At least I'm not aware. I know that Raquel Hurtado, for instance, they were doing some papers on cautious strategies, decision-making strategies for autonomous vehicles, in which you have like you're more committal in the short term and leave your options open in the medium term. So in next like half a second or second, you're not so concerned about what kind of decision you make, but then you're more cautious when it comes to the medium term. So there's a connection there between uncertainty and the temporal dimension, because it really matters what decision you're making now, but it doesn't mean what decision you're going to make in 5 or 10 seconds. You sort of have a bit more leeway. So this is an example I can think of.
Yeah, but I think the theory there is fun.
Not sure there is a theory about this.
Yeah, I mean, we have some applications in cloud computing where it could do things like where eventually we want to either do you take an action to collect information like in a banded sense, but then you may pay some cost, or you can like act and take decisions optimally. Just so there is like some loose connections between explore, exploit, and things like that. But I'm not still seeing is there a principal way to write down like sort of decision making problems where we have uncertainties and possibly maybe the uncertainties are not exact and so.
Yeah, just
Yeah. That has to be should.
Yeah, so maybe one opinion on this discussion of video or self-driving cars or language models and things like that is that we need to think about how to define new notions of uncertainty for such complex tasks. Because I think like a lot of theoreticians do is start from frameworks, creedal framework or calibration or conformal or things of that kind, and try to reach the application from ground up, and then apply people to just ignore what we're doing here, and they start with their application and they try to do something that works for them. But I think what would be nice if as a theoretician actually embedded themselves in the application and asked, for this application, what's the right way to quantify uncertainty? And even the most simple question of how do you define script Y? What's the output space is not obvious. So for example, for language model, should it be the next word, the next 3 words, the next sentence? Or in fact, should it not be on the output token space, but on a semantic space of meaning? I'm uncertain about the meaning of the question, the meaning of the answers that I'm going to build, not really on the tokens. Similarly, for self-driving cars, it's unclear if you should be representing uncertainty on the pixel space or at a higher semantic space of the objects that are represented in those pixels. And so we just often say, well, there's script X and script Y, and somehow that's God gave us that and we go with it. But I think like the right answer that will work well in these applications must somehow start from the applications. So yeah, I think I'm less bothered by the plethora of notions of uncertainty. Like I think we do need to find connections between them. But what bothers me more is there's a big gap between why language models people or people in self-driving cars not use the stuff that we do. Well, they don't really know how to. They don't know what's the right way to define the problem to make any of these tools applicable, and that seems to be an important part of it. But task specific and domain specific and so on.
Yeah, thanks. I just wanted to throw in the additional aspect of model misclassification, which I feel we are treating sometimes rather en passant. I mean, for example, conformal prediction for a non-conformity score to be meaningful, you kind of assume a model that produces meaningful predictions, right? So I have the feeling that we should also incorporate this point a little more into our uncertainty, because if we have like a completely misspecified model, what is our uncertainty estimation worth?
So I'm not sure that conformal prediction makes any assumes a specified model of any kind. Like the non-conformity score is kind of model independent. So if you're doing a regression task, it might just be y minus f of x, like you're just an absolute value of y minus f of x if you're doing a simple regression task. But somehow the task defines the non-conformity score. But and so it is somehow robust to the model that you use. The model being the machine learning algorithm, you used a linear model, but maybe the true model was non-linear. The method still quantifies uncertainty correctly in the end, even if the algorithm that you trained had nothing to do with the actual, like you used a conditional distribution for y given x, which was linear, but maybe the true model was non-linear. Conformal prediction still works in the sense that it'll output slightly larger sets than ideal. So somehow it accounts for model uncertainty. But maybe I agree on a broader principle. Maybe outside of conformal prediction, it is true that we do need to take into account model uncertainty more explicitly.
Okay, shall we call it a day? I think that was very interesting discussion, to be honest. If it wasn't 6 in the evening, I could go on. All right, so the last thing to do is for me to thank two things. Thank all the invited speakers and the authors of the papers, including the Best Paper Award and the Best Student Paper Award. And all of you who are here, and you made this workshop very interesting and possibly the first one in a series, and we'll see. And the second thing to do is to actually hand out the paper versions of the awards, which I believe come with the monetary value attached to them. So one, let's start from the Best Student Paper Award, I think. This is sponsored by, remember which? Yes, no, it's sponsored. Okay, one of them is sponsored by UAI itself, and another one is sponsored by a different source, which I don't remember at the moment. I think the Korea University, Korea Kyungpook National University. And so in particular, the Best Student Paper Award goes to EARL, a representation learning benchmark for transferable uncertainty estimates by Michael Kirchhoff, Badint Mukshani, I hope I'm pronouncing it right, Seong Yoon Ho, and Nicoleta Castellci. So please come forward. Somebody can take a picture.
I think it was a very cool selection, of course. I've written down a lot of things, overview like this, we are very applied thing and the view and stuff. Very cool things.
Hopefully, this will spur a lot of connections and cross collaboration among all these groups. So that's our hope. The Best Paper Award goes to Joint Modeling for Uncertainty Quantification by Chunding Ji, Dingwei Gong, and Meiying Zhang. So please come forward. I'm sorry, it looks small, but it's actually a pretty important one. And you will also get an electronic version. As for the monetary award, you will receive communication from us in the near future. Okay. Okay. So I think that's it for the day. So thanks everybody for attending, and hopefully see you at the next conference for the next series. So keep in touch.
Fabio, I just forgot to also mention a couple of names here. So this workshop was not. Excuse me, I just forgot to show the last slide because behind of me and Fabio, there was team working on this. So let's also give big hands for them, especially Mariam, Kaijin, Shiri. They did a lot of works. So please give them.
Please get in touch with us if you want to collaborate with the project.
Yes, this is the contact.
Especially